Ever tried dividing a cake equally among, like, 7 people? It's tricky. And it kind of shows why we need more than just whole numbers, you know?
Yeah, definitely.
So today, we're diving into rational numbers using this math chapter excerpt you provided.
Right.
We'll see how these numbers are essential for, well, everything, from baking to, like, understanding statistics and stuff.
Absolutely. When we really think about it, our need for rational numbers, it comes from the limitations of just using whole numbers.
Mm.
Imagine, like, baking with only a 1-cup measure.
Ooh, yeah.
You can make some things, sure, but you miss out on the precision of those fractions, those ratios that make a recipe, really shine.
Totally. Like, our mathematical recipes needed some new ingredients, and the source, it talks about closure.
Like closure.
The idea that when you add or multiply numbers, you should get another number in that same set.
Exactly. And whole numbers are great for that. Add them up, multiply them, you get another whole number.
Makes sense.
But then you try subtraction or division.
Uh-oh. Things get a little more complex, right? That's where those rational numbers come in.
Okay, so let's go back to that cake. We need a way to represent those pieces smaller than a whole, those exact ratios.
Yeah.
And that's rational numbers. They give us the tools to divide things fairly, measure accurately, all that good stuff.
And that's where it gets exciting. With rational numbers, we're not stuck on those whole number steps on a number line anymore. We can have half steps, quarter steps, you name it.
It's like having a more precise set of measuring tools, right? Exactly. Just like a baker needs those fractional measuring spoons for a perfect cake, gives us a new level of precision.
Love it. Precision baking, precision math. So we've got these rational numbers, these ratios helping us get those in-between values.
Right.
But there's more to it, right? Like the source mentions some specific rules about how they work.
Absolutely. Just like, a good recipe has its instructions, rational numbers have their own properties. We touched on closure.
Right.
But the source also gets into commutativity, associativity, identity elements, even inverses.
Okay, I'll be honest. Some of those sound kind of like straight out of math class, haha.
Right, haha. But trust me, they've got some real-world stuff going on behind them.
The source does break them down well, I'll give it that. Like, take associativity. Basically, it means you can group numbers differently when you're adding or multiplying and still get the same answer, right?
Exactly.
Like, 2, 3, 4, it's the same as 2, 3, 4.
Exactly. It's about that flexibility in grouping.
But here's where it gets kind of weird. This whole associativity thing, it doesn't always work with division.
Good catch.
Oh?
And the source, it gives a really clear example to show that.
Yeah, for follow-up.
If you divide 12 by 4, then divide that by 2. It's different than dividing 4 by 2 first than dividing 12.
So, okay, why does that matter? If a property like that doesn't always hold true, what's the takeaway?
It shows how important order is, not just in math, but, life in general.
Yeah.
Think about calculating a discount.
Oh, okay, yeah.
The order you apply those percentages. Big difference in the final price.
So that whole order of operations thing they drilled into us in school, PEMDAS or BODMAS, whatever, it's not just some random rule.
Nope, it's all based on these fundamental number properties.
Well, okay, so we're not just avoiding math errors, we're being mathematically consistent.
Exactly. Whether it's some big equation or just figuring out the best deal at the store. Makes you think, huh.
So we've talked about why we need rational numbers, these ratios, to get those in-between values and those rules, right? The properties that govern how they work.
Right.
But how can we actually picture these numbers?
Well, the number line's great for that. Think of whole numbers as those clearly marked points.
Okay, yeah.
But then all that space between them.
That's where it gets interesting.
Exactly. Our source really stresses that between any two rational numbers, no matter how close they seem, you can always find more.
So it's there's always more no matter what.
Always. It's called the density of rational numbers.
Yeah.
Mind-blowing, right?
Totally mind-blowing.
Take the example from the source finding rational numbers between -2 and 0. We could start with -1, halfway between.
Makes sense.
But then we could find another between -2 and -1, like -1.5.
Oh, right. And then another one between those two and so on and so on.
Exactly. It's like zooming in on a picture. The closer you look, the more detail you see.
Whoa. Okay. I like that analogy. So we've gone from dividing cakes to exploring this infinite world of numbers. It's pretty amazing how something that seems so simple, these ratios, can be so complex too.
It really highlights how math is full of surprises. And even within simple ideas, there are these hidden depths waiting to be discovered.
This deep dive has really shown that rational numbers aren't just about fractions and equations. It's a whole new way to understand and measure the world around us. It makes you think, Like, what other hidden depths are out there? That's something to ponder, right?
Absolutely. There's always more to learn, more to explore.
Couldn't have said it better myself. Thanks for joining us on this deep dive into rational numbers. Until next time.